what will be the value of u of n at 3? At 3. So I was talking about equation 158. I don't know, right now it is actually, my screen is full. So I will try to have some of these things. And I'm saying that I had tried to do this just briefly so that I can show you how it comes about. And here is the idea that you want to express the unit step using the unit impulse. And we are saying this is the definition. You can actually prove this by setting your n to be 3. So you're going to be adding 0 from minus infinity all the way to 3. So assume your k is -1 or -2. What will happen? When k is equal to -2, the delta function of -2 will be what? Of course, I was hoping someone will speak, but nobody is speaking. Of course, the delta function of -2 is 0. Because we said that it is only, we normally use square brackets. If it is -2, this is equals to 0. -1 is equals to 0. But when it only becomes 1 when the term in the bracket is 0. So the -0 will be 0, the -1 will be 0, and the del of 0 will be 1. So the first term, or the term at n is equals to 3 is equals to 1. Then the others are 0, 0, and 0. And you can also evaluate it. So of course, when you add all these, they will simply give you a 1. So we are saying that evaluating u of n at 3, you know what we know about, I'm trying to take advantage of this so that you can see as clearly as possible what we're talking about. Let me add this space here. And just as we did before, we are saying that my drawing is getting messed up. Okay, so we can always now mark our points: -3, -2, -1, 0, 1, 2, 3, 4, etc. We are asking ourselves, what is the value of n? And we have seen it is expressed as n, k is equals to -infinity, del of k. That is how we are saying that we express the unit step function in terms of the unit impulse function. And we have said we want to evaluate. Okay, before even there, we know that if this is my 1, we know that unit steps takes the values like this one. Going to be 1, going to be 1. Everywhere else is going to be 0, 0, 0. So this is the unit function. This is u of n. But assume you want to evaluate u at 3, meaning that n is equals to 3. We're saying this is going to be equals to sum of k from -infinity to 3, del of k. And we have said del of negative, assuming you can go all the way from -infinity. But I'm assuming let's start at -3. You see, there of 3 is equals to 0. There of -2 is equals to 0. There of -1 is equals to 0. And let me ask someone now, Wilfred, let me allow you to, let me unmute you so that you can speak up. You can tell us the answer. Okay, now you can unmute yourself. Wilfred, it's your chance. What is the there of 0? Very quickly. You're waiting.
I think there should be 0 as well.
No, it's not 0. Godfrey should be around. Godfrey?
Supposed to be 1.
Correct. It's of course supposed to be 1. That is what we have said. And I hope now that becomes clear to everybody. That we are saying that this term only becomes 1 when the term in the bracket is equals to 0. So we are therefore saying that we are going to keep on saying, now the other one that we are remaining before we go to n equals to 3 is delta of 1 is equals to 0, delta of 2 is equals to 0, and delta of 3 is equals to 0. So the only term for the summation will be this term. So when you add all of them, you get this is equals to 1. And that is as we expect that at 3, at n is equals to 3, my u of n is equals to 1. So that is where we are, and I know we have really spent time there, but I think we can now carry on before things get too much. So this, okay, I think I can map this now. We're saying that using equation 146, any sequence x of n can be expressed as equation 151. And that is important also. And actually, that is the term I was using too before, that you can always express any equation or any sequence using that equation. And it simply works out. I hope you find some time to prove that to be the case, because it will show that to be a very useful expression. And it corresponds to the continuous time sequence that we define in equation 157. He also said something like that, but now it was in the integration rather than in summation. And I believe it was saying something like this: x of t can be expressed as integral from -infinity to positive infinity of x of no, it's not positive infinity. It's supposed to be, I think, infinite tau. D of t minus tau d no, d tau. So you can confirm if that is the case. If they have missed something, you can always let me know. So these two equations are actually similar, and one is in the discrete time, and the other one is the continuous time. And now we jump to complex exponential sequences. And remember, we are going through the same kind of sequences as we did with the continuous time. We have dealt so far with the unit step function and the unit impulse function. And now we are jumping the complex exponential functions. And now in this case, instead of using omega naught t like we used in the continuous time, we are using ohm naught t. Okay, not not t, but rather ohm not n. To express as shown in equation 152. So having said that, we are saying that using the Euler's formula, we can be able to express equation 152 as a sum of the real term and imaginary term. This is, of course, using the Euler's equation. And for the case, for those people who keep on forgetting, this is how you break it down. Cos theta plus j sine theta. So once you write that down somewhere, it will always become easier. Now our theta in this case is equals to ohm naught n. Therefore, you can always be able to break this down like that. So thus, x of n is a complex sequence whose real part is cos of ohm naught n, and the imaginary part is sine ohm naught n. And you can discuss the periodicity, which is another interesting discussion. I will avoid moving in that direction because time is running out. But look at it on your own, and you will see how applicable that periodicity is. When we talk about periodicity, we are just saying how do you determine if a sequence is periodic or not. These figures are expressed after in the next page, so we'll come back to them shortly. So this is the continuation on periodicity. We will not discuss them further, except that after you have gone through the periodicity and observing some expression like this one, you'll observe why when you're discussing discrete time signals, we normally set our limits instead of going from infinity to, like we are saying, minus infinity to positive infinity. This is with continuous time. With discrete time, we normally set our limits from minus pi to pi, or we also express them as from 0 to 2 pi. So the reasons behind why we not normally use these two terms is it's explained with the periodicity of complex exponential sequences that we have just skipped, and we have just skipped in the interest of time. So, and we can now look at a general complex exponential sequence, which may be expressed as in equation 157, right there. And we are saying that C might be complex, as well as A alpha might be complex as well. So if that is a possibility, then we are simply saying that equation 157 or equation 152, which is up here, I'm not very far. Equation 152 is the one that was defining the complex exponential sequence here. We are simply saying that this is expressed as in a special form of complex exponential sequence that takes the form C alpha power n, where we are saying that C in this case, C is equals to 1, but alpha is equals to E j ohm naught. Yeah, j ohm naught. So so that is where we are. We are saying that we can be able to express a more general exponential sequences as expressed in equation 157. And as I have illustrated, C is equals to 1 equation 152, and alpha is equals to 1 exponent of j ohm naught, as we have just seen. And very briefly, we are going to identify a sample sequence expressed as cosine of pi over 6n. This you can look more keenly on your own, but what you'll observe is that this is a cos function, cost function that is periodic. Okay, it's a cost sequence, it's a sequence that is developed from the cost function. And this term here determines whether the sequence that we get is periodic or not. As you can see, it is possible to get a periodic or a repeating sequence by just assuming that you can join those dots like that. What you'll observe is that this is periodic, meaning that you can be able to get a similar signal when you increase the period of your function. But on the other hand, cos of n over 2 that we are seeing down here, this is actually not periodic. Because assume you want to redraw a sequence here, you actually have some points of discontinuities, and if you actually say at point 0, this might be, let's say, a value of course, even looking at this diagram, you can see here we have a value, and here we have two values that are maximum. Here we have two values that are maximum. This one is 1. This one is 1, but then the value that is here is different from the value that is here. And what we are simply saying that if you are trying to identify what is the fundamental period of this signal, it will approach infinity. And we normally say that for a signal to be defined as periodic, it must always be less than infinity. So therefore, because this condition is not determined, or it is not does not evaluate to be true, therefore we actually see that this signal is not periodic. And that is a very important factor. And I think there's somewhere in our conclusions that we are making that statement, that you might have a periodic signal in continuous time. When you sample it, you have a non-periodic signal, a discrete sequence. So we're saying that this is a possibility, and there are some mathematics that we will probably meet as we do our tutorials that will show this to be the case. And that is a very significant point. So that was about complex or general complex exponential sequences. But now looking at a real exponential sequence, we are simply saying that when alpha is, when C is a non-complex or it's real, and alpha is real, then we just get a real complex sequence. And sinusoidal sequences, just like we have been doing, is can be obtained similarly like we did in continuous time, can be obtained as you can see in question 158. And simply we have this term that is a function of cosine. And we are saying that n is dimensionless, and theta or ohm naught and theta have units of radians. And the two examples of sinusoidal sequences are shown in figure 1.1.3. And actually, it's actually here. So these are the ones that we have just talked about. And as before, the sinusoidal sequences in question 158 can be expressed using the Euler's expression. Remember, we said that you can be able to say that Ej of theta is equals to, has the real part, or which is Ej of theta plus the imaginary part, which is Ej of theta. And this is actually the cosine of theta, and this is the sine of theta. So again, breaking that down actually gives you equation 159. As we have observed in the case of complex exponential sequences, in equation 152, the same observations about 154 and 156 also holds for equation 1 for sinusoidal sequences. So this is about the periodicity that we skipped. And that bit is the one that explains what we have just said, that the first function is periodic, while the second one is not. So, and that is the point I was trying to say, that you might have a periodic function in continuous time, and you might sample it in a way that will cause it not to be periodic in discrete time. So that we are almost done. The longest part is what we have covered. I hope to finish this in the next 10 minutes to discuss the systems and classifications of systems. As I mentioned today, we had a lot to cover. So we are going to move pretty fast and finish up. So we are going to say now that a system is a mathematical model of a physical process that relates the input to the output, or relates the input signal to the output signal. Or in other words, it relates the input, which is an excitation, to an output, which is a response. So in few words, this is how we normally talk about, this is an example of a system. It has an input X and output Y. And you're saying that if you let X and Y be the input and output signals respectively, then the system is viewed as a transformation or mapping of X into Y. So you might have a signal, it is simple, like consider you have a mic or a microphone. You are speaking here, like I'm doing, speaking, Isaac is speaking. And on your side, you assume you have a speaker that is, you can hear, this is the output, sound, you can hear some sound. So of course I send some sound here, but then something happened to the signal, it came out. Probably it was amplified, probably it was filtered, etc., etc. So that kind of system that modifies the input to give you some different output is the one that we define as a system. And we are saying that a system consists of an operator. And the operator can be defined in mathematical notation as having symbol T, which is the function that operates on the input to give you the output. And we're saying that it has to be well defined so that we can get a proper relationship between the output and the input, and the input and the output. And relationship 160 is depicted as shown in figure 14a. And we might also have a multiple input and multiple output signal as shown in figure 14b. But for our business or for our classes, we are going to be dealing only with single input, single output signals. They are the multiple input, multiple output systems. We are not going to be dealing with them for now. So that is the first classification. Of course, that is the first definition that we needed to do. And now we go now to classifications of systems. And the first classification is the one that, of course, there is still a classification that says that this is multiple inputs, multiple output, and this is single input, single output. That is the first classification of systems. So the second classification of systems that we are going to be talking about is the one that deals with continuous time vis-a-vis the one that deals with discrete time. And the continuous time is, as you know, it acts on a continuous time function, and it outputs a continuous time output function. And the discrete time signal operates on discrete time signals and operates on or gives out discrete time output signal. I can see that there are some people who have audio, so again, I will mute them so that we don't get some audios coming. And therefore, we don't get any interruption. I have just muted everybody, and just for the sake of reducing the interruption. So now, that is the other classification that we just went through. And the other one we are going to be talking about in regard to the classifications of systems deals with a system either with memory or without memory. And again, a system without memory is the one that the output depends only on the input at the same time. Like what I'm putting out, okay, what I'm putting into the system at this time depends only on what I put it in and not what I put it earlier. And I think the example is that of a resistor. The current that flows in a resistor is only dependent on the immediately applied voltage, not the past one. So that is in regard to a memoryless system. But a memory system is like that of a capacitor, whereby the current, like you apply some current to a resistor, then the output is a function of the present input and some past input of voltages, and therefore over time it is going to know that like you have given me this current now, and after some seconds you have given me this current. So if you want to measure the voltage after some time, it will be a function of the past input and the present input, and that defines a very clear category of systems that are either having memory or without memory. And examples are resistors, flow of current is memoryless, while that of the voltage from a capacitor is having memory. And we are saying that you can express a system with memory, as you can see in equation 163. And we are saying that the output y of n is dependent of the present input, which is n, and other past inputs, which started from infinity, like long time ago. We have been accumulating, and therefore that says that illustrates the concept of a system with a memory. Now we jump to another one that is classified as causal or non-causal. And with causal systems, we say that the present input, the present output depends on the input that we have just put now or in the past. There might appear like there is a cross relationship between causal and non-causal, but they are quite unique. So we're saying that for a causal system, the output at an arbitrary time t0 depends only on the input presently and in the past. And the key item here to observe is that a causal system does not depend on some future input values. So that is the major distinction, that if a system has no past inputs whatsoever and no present input, and yet it has some output, that is not a causal system. So thus, a causal system it is not possible to obtain an output before any input has been applied. But we're saying a non-causal system is not causal, of course, and you're saying that even before you have put anything, there is no past or present inputs, yet it will give you some values. And we are saying that the examples of a non-causal system is the one that you see here. It's the one that you see on equation 164 and 165. that even before you have applied any value of input, you have some future outputs. So that is the major difference. And we are saying that not all memory-based systems are causal. I told you there is some relationship. All memory-based systems are causal, but not vice versa. So you cannot say that all causal systems are memory-based. That is not the case. And almost finishing, my note time is running out. Linear systems and nonlinear systems. We are saying that if the operator T in equation 160, the one we defined earlier, satisfies the condition below, where T is the linear operator, then the system is said to be a linear system. And the equation that we are referring to at 140 was saying that Y is equals to Tx. So this was our linear operator. And this was our input, and this is our output. So we are saying that if this expression or this T follows these two conditions that we are about to define, that of homogeneity and additivity, then our system is said to be linear system. And the one for additivity means that if the one input is a function of input x1 and y2 is a function of x2, then if T acts on x1 and x2 at the same time, then the sum of the output will be y1 and y2 at the same time, like the sum of these two. That means that if you act, just a minute, someone needs knock at my door. We're about to finish. Sorry, someone knocked on my door and I needed to attend to them. So as we're saying that as long as the two conditions are satisfied, the first one being that if the system acts on the signals or the input signals are together, and it gives the output as though it was the sum of the individually operated on inputs, then that system is said to have to obey the condition of additivity. And the second condition is that if you multiply your input with a scalar alpha, and then you take that system into, that input into your system, and you find that the output is a function of alpha, then you can say that it obeys the condition of scaling. And then you actually say that the system is a linear system. If it doesn't obey that, then it is not linear system. And those two conditions can actually be put together, expressed as you can see in 168. A nonlinear system is we have said is actually similar to the one we have said about a resistor and a capacitor. So those two systems are said to be linear systems. Now we have some example of nonlinear systems here, that one of them is x squared and cos of x, and you can actually try to try that out. If you take your x to be 2, or x1 to be 2 and x2 to be 3, and you assume your t is equals to 10, then your y1 will be equals to 20 and y2 will be equals to 30. If you add the two, the output will be 50. But now I'm trying to evaluate the condition of additivity together with the additivity. If you now act on the two systems and say that t, y is equals to t, 10 to the 1 plus 1, Actually, I might actually lose you people. Actually, the examples I'm giving you will not work. So for now, I will withdraw that example, and I say that a system that follows the condition 168 is linear, and the one that looks like this one that doesn't follow this condition is nonlinear. And here is the point that we are saying is that the consequence of homogeneity or scaling is that if you have a zero input, you have a zero output system. So there is one more classification that we need to look at, which is time invariant or time varying. And this is something you can even read for yourself. I don't want to push you beyond the time.